Hello and welcome back to my YouTube channel, a place where you come to learn about numerical methods. Today we'll be learning about linear and nonlinear regression, which is one of the most popular ways to fit a set of data points. So in this method, what we do, we propose a model to which we do a least squares fit. So we'll learn more about the measures here. Popular measures are the mean absolute errors, the mean squared errors, and the root mean squared errors. Then you check the covariance using the R squared and the adjusted R squared. So let us start with the linear least squares method. So in this method, we want to fit a set of data points using a straight line. So we propose a model y bar which is equals to mx plus c. Our goal is to find the best possible m and c. So for that, first we define the definition of a residual. Residual is y minus y bar. Then we take the square of this residual. So you can visualize by adding these area of these squares, and we want to minimize such a way that the global sum of squares is the minimum. So we define the problem, then we take the partial derivatives with respect to m and c and set to 0. Now these two simultaneous equations are linear so that we can easily solve for m and c. So here we form a matrix system. These are the coefficient matrix, parameters, and the constants. The closed form solution is as follows. So you can easily calculate the values for m and c using only the data points given. An alternate form using the variance and covariance is also given. In the sense of matrix notation, what we try to do, we have an overdetermined system and we want to solve for it. It's a rectangular system, so we want to convert it into a square system by multiplying by its transpose. Now we can easily take the inverse. Now this complete part is now called the pseudo inverse. This pseudo inverse has a very big role in the least square systems. So if I want to solve for a least square problem, we design this problem in such a way that y is equals to x beta. Then we take the transpose and multiply by it and then take the inverse. Now this final solution beta is the least square solution for this particular problem. For nonlinear systems, this becomes a little bit tricky. So now you have a nonlinear equation. Let's say you have a e to the power bx. Now we want to calculate the parameters a and b in such a way that again the squared sum of the residuals is minimized. So now by taking the partial derivatives, we are not able to get to a linear system of equations. So what we do, we try to design a nonlinear system and solve using the nonlinear methods like the Gauss-Newton and the Levenberg-Marquardt methods. In the Gauss-Newton method, we solve by linearizing the residuals. We do a first order Taylor series expansion of the residual, and then using that Jacobian information, we evaluate the corrected step. So now this change in theta is calculated by solving this linearized problem and then updating for the current step. Now this LM method is also called as damped Gauss-Newton because it adds an additional damping parameter lambda multiplied by the D matrix. D is typically the diagonal of J transpose J or the identity matrix. And now this lambda is adjusted dynamically so that we get to a better convergence rates. Now let us quickly go to MATLAB and try to implement all these things using the Curve Fitter app that is inbuilt in MATLAB. So first what we'll do, we'll create some data sets. So I'll create x1 which is length space 0 to 5 in 50 steps. So it creates a linearly distributed points from 0 to 5 and the number of points is 50. Now I create a perturbation parameter epsilon. Now epsilon is 0.25 times the random matrix of size 1, 50. You have to be very careful that the size of x1 and epsilon has to be same. Now this RNG command, this fixes the perturbation parameters so that when you rerun the program, you don't get different parameters. You don't get different random variables. So for the first function, I create a straight line, which is 2x plus 1 plus epsilon with some perturbation. Now this 2x plus 1, we should be able to capture using linear regression. Now this line equation with this perturbation, as you may expect, will have a slightly different equation of line by linear regression than what is given here. For the second set, what I'll do, I'll create a sine wave. I won't be adding perturbation in this example. So what it means that if you have a very smooth function, what I'll be trying to show it to you that if you have a very smooth function, then you can approximate it using a very high order polynomial itself. You don't need to get to very fancy functions. A polynomial fit would be good enough. Now for the third example, what I'll do, I'll create an exponential sine wave so that it does not fit using sinusoidal function. So as you'll see later on in this video, that there are multiple options available in the Curve Fitter app for the linear regression type. So now what I'll do, I'll create the fourth example. Now fourth example is for an exponential function. So what you'll see that you have the Fourier functions, the sum of sines, the exponentials, the logarithmics, the polynomials. You have an array of options in the Curve Fitter app. So I am trying to create examples in such a way that you are able to use a lot of those options while we are experimenting with them. Now for the final case, I create a random function which is a sum of 8 sine functions. So you'll see that it has different peaks at different time intervals. So now just to give you a quick visualization, what I'll do, I'll just plot all these functions by adding the plot command and giving it a run. So as you'll see on the right hand side that there is a lot of different array of functions which we are going to try to fit. So let us now just save this file with data.mlx and then open the Curve Fitter app. So we go to apps here and then we go to Curve Fitter. Now in this, what we do, we create this file name with fit1. In the x data, I call x1 and in the y data, I call y1. So this, as you remember, was a straight line 2x plus 1 with some perturbation added. As you can see that there is a lot of perturbation here. So here you can see the polynomial degree and here you see the coefficient values and you see that it is slightly off by 2 and 1 just because we have added some perturbation. Now these are the confidence bounds of 95%. And from here, you can change the confidence bounds from other values other than 95%. And from here, you can add the residual plots and you can see for each individual point what is the value of the residual. Also, if you want to export this image, then you can go to this point and then export it to figure, or you can also export the code or the data to the workspace. So what I'll do, I'll just export it to figure. Now I can also change this figure if I want. I can just select this parameter so that these legends are not obstructing my original plot. So I'll just manipulate this and then I'll just save. I'll save this as figure 1. I am currently saving it as a MATLAB figure.fig. I can also save it using some other format. There is an array of formats here. And what I personally prefer is a .svg, the scalable vector graphic. Now for the second case, I go here and then select the new fit. So I am getting a next tab and again I am selecting data. I rename this as fit 2. Again for the x1 data, I am taking x1 and for the y data, I have to take y2 now. Y2, as you remember, was sine 2x. So it cannot be fitted by a straight line. So if I now increase the order of the polynomial, you'll see that the RMSE is reducing. As we keep on increasing the number of coefficients, the RMSE decreases. root mean squared errors. So now if I keep on increasing the polynomial orders, you'll see that you get a very good fit. This is the characteristic of a polynomial fitting for smooth functions. And you see that there is an array of functions available here. And if I just take it as a sum of sines, because it is already a sine function, I can capture it exactly using only one term. So instead of using a higher order polynomial, if at all I had an information that it was a sine function, then I can do a judicious fit. And the RMSE is very low. So what it suggests that if you have a basic idea about which type of model your data is likely to be fitted with, then you can use it to your advantage and it can save a lot of time. Again, checking for the residual plots, it is of order 10 to the power minus 5, which is very small. Now, what we do, I'll go to the next fit. Again, I'll create the new fit. Then I'll select the data. I'll have x1 in the x and then y3 in the y. As you remember, it was an exponential sine wave. So the amplitude is varying as we increase the x value. So if I want to try to fit it using a straight line, it is not so likely to get a very good fit. So what we'll do, we'll try to fit it using some other method. So what we'll see, let's say, I'll take the exponential part. So for exponential, here you have options for two terms, up to two terms. So if you are taking up to two terms, you don't see it visually that you have a very good fit, and even the RMSE shows that. So now let's go to, let's say, Fourier. For Fourier, it is a sum of sine and cosine series. So, and we have the number of terms can go up to 8. So you'll see that even with only two terms, you are getting a very good fit visually and through RMSE. This means for this type of exponential sine, cosine functions, and if you have a multiple combination of those, then fitting it using Fourier series would be a good option. Now let's go to the new fit and then go to the fourth option. Fourth option was just a plain exponential function. So again, I'll select x1 and y4. Now you'll see that apart from the exponential function, you have also added some perturbation. So now with two terms of exponential, we are still not able to converge because of that perturbation parameter. Let us now try to fit it using polynomials. For degree 1, you see that it is of no use. And by increasing the order of polynomial, we see that there is an improvement in the fit. But again, due to this perturbation, you see that there is not a very good fit. So even with the sum of sines, if I take the number of terms to be 8, again you will see that there is a fit. There is some improvement in terms of polynomial fit, but it does not converge. It does not converge below the tolerance. So this perturbation is causing a lot of issues. So what we can do, we can use the exclusion rules. We see that the perturbation is more after x is greater than 1.5. And for x less than 0, we don't have any data points. So I'll just have this condition for excluding the values which is less than 0 and more than 1.5. Similarly, I can do for y. So now you see that you have a very clean data. And now if I want to fit this data by just a straight line, I'll go to polynomial, I'll go to degree 1, and you'll see that it almost fits. So now in terms of RMSE, you get this value. And if I go to just a cubic polynomial, you see that the fit improves drastically. So you can also use this exclusion rules whenever you have some data points which is very far off. Sometimes it may happen that in your results, you have some data points and which you want to exclude. So keeping that apart, now let's just go to fit 5. And again, taking x1 and y5. Now this was the sine wave with different amplitudes. So one term won't be enough. and I'm going up to 8 terms, and you see that this becomes a very good fit. The RMSE value is very small. So this is what you can do with a judicious use of your basis function. So I'll now just save this. I'll call this tutorial 1 and then save this. So now this is an SFIT file, right? So you cannot open it directly, but when you open the Curve Fitter app, then you can open it using the open command. Now you'll see all the fits that we have done, all the 5 fits is shown below. And you also see which fit type was used, what are the residual values, what are the RMSE values, what are the number of coefficients. All these values can be looked up in this below table. And again, if you want to export those images, we have already checked how to export this. And all the confidence bounds, all the parameter values, all the coefficient values are shown in the bottom right part. Thank you so much for watching, and I'll see you next time. Thank you.